Hi, in this video we'll be discussing about heat transfer through a plane wall. So here, in order to understand this heat transfer through a plane wall, first of all let us consider certain assumptions. So when we talk about this heat transfer through a plane wall, we need to consider one dimensional steady state and without internal heat generation. One dimensional means we will be considering only in the x direction here. So let us consider there is a plane wall like this. So this y-axis represents the temperature axis and the x-axis represents thickness or the distance x. So here as we are considering one dimensional, so therefore no need of considering the other two directions, and let us consider simply this particular diagram to understand heat transfer through a plane wall. Now let us consider the thickness here as L, and in order to understand this particular formula of heat transfer, first of all we need to set certain boundary conditions. So here let us consider this side of the wall is at temperature T1 and the other side is at temperature T2. So therefore the boundary conditions that we need to consider here is that at x is equal to 0, the temperature T will be equal to T1, and at x is equal to L, the thickness, temperature is T2. So in order to have heat transfer, T1 is greater than T2, let us assume. So therefore heat flow takes place in this particular direction. Now here the goal of us in this particular thing is that we need to understand how will be the temperature distribution within this thickness, and suppose if at some distance within this thickness we want to determine temperature. So how can we determine that temperature T, and what is the heat transfer? These three things we are going to analyze in this particular case. So therefore, in order to analyze all these three things, we need to take the fundamental equation, that is d square t by dx square plus d square t by dy square plus d square t by dz square plus qg by k. This is equal to 1 by alpha into dt by dt. Now this equation is the general heat conduction equation in Cartesian coordinate system. So as we are considering one dimensional condition, we need to eliminate these all things. So therefore, as we have considered one dimensional steady state heat conduction without any internal heat generation, we have eliminated all these parts, and finally the equation reduces like this: d square t by dx square is equal to 0. Now our condition is that we need to determine how is the temperature distribution. So therefore we need to get this particular equation in terms of temperature T. For that we need to integrate this twice. On integration for the first time, we are going to get dt by dx is equal to C1. Let us put it as equation 1. Now again integrating this, we are going to get T is equal to C1x plus C2. So you need to understand this part carefully. So here you can observe that this is similar to y is equal to mx plus c. So that means this is indicating a straight line equation. So therefore we can consider the temperature distribution temperature distribution here is linear. So this is the most important point which you need to understand here. Then, as we have got the temperature distribution, now we need to substitute the boundary conditions in order to get the values of C1 and C2. The boundary conditions are: at x is equal to 0, the temperature T is equal to T1. So that implies T1 is equal to C1 into 0 plus C2. From this simply we got C2 is equal to T1. This is equation 3. Now the second boundary condition we need to substitute. At x is equal to L, the temperature T is equal to T2. So therefore we get T2 is equal to C1 into L plus C2, already we have got it as T2. So from this, already we have got this as T1. Sorry. So we need to take this as T1. So from this C1 we are going to get T2 minus T1 by L. This is equation 4. Now let us substitute equation 3 and 4 in 2. So therefore we will get T is equal to T2 minus T1 by L into X plus T1. So this is equation 5. Now from this equation we can determine temperature at any point X. So temperature at any point X can be determined by using this particular equation. So here we need to consider that the temperature distribution is linear, and in order to determine the temperature at some point X, we need to use this particular equation. So to remember this equation easily, we can write like this: T minus T1 by T2 minus T1 is equal to X by L. So this will make the equation easier to remember. Now, the third thing that we need to determine here is about what is heat transfer. So we have learned that heat transfer Q is equal to minus Ka into dt by dx. So here dt by dx is nothing but C1 from the equation 1 which we have got. So therefore minus Ka into C1 value we have got T2 minus T1 by L. So therefore from this we can write Q is equal to T1 minus T2 by L by K. So this is the formula for heat transfer when we consider a plane wall with one dimensional steady state heat conduction without any heat generation. So this L by Ka is nothing but the thermal resistance due to conduction. So this equation is similar to that of the Fourier's law of heat conduction, and the assumptions made here and in Fourier's law of heat conduction are same.